Very good morning, class. Today we're going to cover example 4. Before we start, I want to highlight what we have learned during the last class. Okay. Basically, we learned about how to calculate the magnitude of resultant force as well as the position of resultant force. We call as the HP. Okay, in order to get HP, we need to find the YCP using this equation, negative Ixx sine theta over HCA. So for this part, I would like to recap with example 4. Okay, so for this one, please stay focused here. A gate AB, length L, width B into the pitch. Okay, so let me take a picture. All right. Okay, so I hope you can see the picture, yeah. So gate AB, you can see A to B length L with B into the pitch is hinged at B and has negligible weight. The liquid level H stay at the top of the gate at the angle theta. Find the expression of the force P perpendicular to AB that is required to keep the gate in equilibrium. Okay, the first step, how to get the equilibrium, we must apply the moment of, the moment at point B. So I want to apply moment at point B equal to 0. Do you know why I need to apply moment at B? Class? Why I don't apply at point A? What do you think?
Derivation force.
Pardon? Tan Binji? Because of what?
Derivation force in y and
Okay,
x direction.
yes, correct. At B, if we don't apply the moment at B, we have to consider reaction force, which is FB in Y direction, FB in X direction. If we consider moment at point B, automatically it is 0. Okay, we don't have any force. That is why we need to simplify our equation. Okay, so in order to get the moment, sorry, I think there is. Okay, in order to get the moment, we must know the force acting at point B. Sorry, we must know the force. So here, we draw the free body diagram. This is centroid. Okay, and then we have the resultant force, okay, at here. Fr. So based on this equation, based on this question, required to keep the gate at equilibrium. So that means the pressure, this must be equilibrium, must be equal. However, when we apply the moment, okay, we must use the moment here. Okay, we must know that the moment, okay, at point B is equal to PL, okay, minus F R multiply with this distance, which is K, FK, okay, equal to 0. And then we can have P equal to FR K over L. Okay, is it clear? So the problem here, how to find the FR? And then how to find the K? Okay, let's solve using our equation that we have used before. In order to get the FR, we use the F equal to gamma HCA. So, gamma of this water is easy. However, HC, how to get the HC? HC is here. From the surface to the centroid. So, this is HC. To get the HC, definitely it is H over 2. You can see here, H over 2. Multiply with the area of this gate AB, which is L multiply with B, LB. And then we will get HLB gamma over 2. Okay, now we got the FR. How to get the K? Definitely we must know the position of this FR position. So using our previously derived equation, YCP equal to negative I, okay, negative IXX sine theta over with HCA. Okay, we know that the IXX, the moment of area for the gate is BH cube over 12. This is rectangular. So B is, you can see here the H should be the total length. And the B is here, the width. So BL cube over width 12. Substitute again in this equation. Negative, okay, negative 1 over 12 BL cube sine theta over with HC, which is H over 2, multiply with area LB. You simplify the equation, you will get negative 1 over 6H L squared sine theta. Okay, so that means YCP is this value, this value. From here, okay, from this point to point, okay, this value, this is YCP. Okay, so from here to here is L over 2. Okay. Thus, just substitute in the equation here that we used before. Okay. F we know. K, how to get the K? How to get the K, class? Anyone would like to try? How to get the K? Fong Yika, Ko Zizwa, Hafizul, Salsabila, Irfan, Tan BG. How to get K? Very simple, I think. I already list there. You need to plus minus only. How to get the K?
half
L over
length
2
of
minus YCV.
Yes, very simple. In order to get K, half L, right? Right. Or L over 2 lah, simple. L over 2 minus with Y, CP. Okay, so just solve it. So K equal to L over 2 minus, okay, this is YCP. You need to consider the magnitude only. The negative we already know. It is below the centroid. So minus with magnitude. Okay, all this 1 over 12 BL cube sine, sorry, this is not. Okay, minus with 1 over 6H L squared sine theta. So you get the K, put here in the equation, P equal to here. Okay, F R K over L. So FR is what? FR we discover it is H L P gamma over 2. And then the K here is L over 2 minus with 1 over 6H L squared sine theta over with L. So you simplify L. Okay, you can simplify here L, only L. Okay, because this is factor. So the answer shall be P equal to, you simplify HB gamma over 2, L over 2, 1 over 6H, okay, L squared sine theta. That's it. Okay, that is the answer. Any question? Class, do you have any question?
No, Doctor.
No, Doctor.
No, okay, good. Okay, let's proceed on the next part, lecture number 4. Okay, the previous class, we learned about the straight or the plane surface. However, how about the curved surface? There is the curve. So when it is the curve, okay, you need to consider X and Y direction. Okay. For this one, I need you to focus, okay? For example, we have the curve. This is the plane, the curved surface. Previous class, this is only the straight, right? Okay, we have the straight surface. Now we have the curve. How to solve the curve? Okay, so now we look at the surface that have some curvature. Compute the resultant pressure force by separating it into horizontal and vertical component. Okay, and then the pressure here, the pressure force are normal to the local area element of the surface. Okay, whatever it is, the pressure force must normal to the local area. The local area means we divide the curvature into horizontal and vertical component. Let's see. We have the curvature. Okay, we have the curvature like this. Okay, this curvature, we must, okay, the first step how to solve this, uh, you must know how to project, to make the projection. Okay, since the pressure force is separated into horizontal and vertical component, we must know how to project this curvature. Okay, from here I project in this direction, the horizontal. This is the projection, yeah, because we need to separate. Okay, and then this is the projection in, okay, the vertical direction. Alright, so here let's name here as the horizontal projection of the curved surface. Okay, and here is on the other hand lah, vertical projection of the curved surface. Okay, and then definitely this is the curve surface. So from here, let's draw the free body diagram of the fluid block. Okay, let's say we take out only this portion. We take out outside, yeah. We only consider this portion only. We take out, and then we draw the free body diagram. So I try to take out. Okay. 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 And then we need to assign the force. So from here we have the force in y direction. Okay, remember horizontal pressure is the same. So the magnitude also the same. So this is Fy. However, for this force, it is not the same because this is vertical direction. Okay, so we call as this one. Definitely will have the resultant at here. We call as the Fx. Okay, this is resultant lah, basically at the center. Okay, and then this is the resultant in terms of x. Okay, excellent. And definitely we have the force here. You can see it's difficult. Okay, we have all the force component acting perpendicular. So from here, based on the incline of forces, okay, we assign here as resultant force. Okay, this is F R. Definitely, we gonna have the F H and F B. Okay, in Y component and X component. So I would like to remark here, FV and FH here basically can be found using F equal to gamma HA. Alright. And then don't forget we have the weight here. The weight of this block. Alright. So the weight of the liquid block is rho GV. I previously explained to you the weight is mass multiplied with gravity. You convert the mass in terms of rho V multiplied with gravity. So the weight is rho GV. So this acts through the centroid of the volume. Okay, perfect. So from here, we can have the static equilibrium. In summation of force in x direction to be, okay, Fh is equal to Fx. And summation of force in y direction will be Fb equal to Fy plus minus W. Okay, that means the weight here, okay, in order to get the force in vertical direction, Fy plus W or minus. You can see the case of minus because it is below the region. Okay. So this is the general rule. Horizontal component of hydrostatic force is equal to magnitude and direction to the hydrostatic force acting on the vertical projection of the curved surface. Number 2, vertical component of hydrostatic force is equal to the hydrostatic force acting on horizontal projection of curved surface plus or minus weight of the fluid block. Okay, this is I will explain lah. So now let's take a look on the example 1. Compute the horizontal and vertical component of the hydrostatic force on the quarter circle panel at the bottom of the water tank. Okay, so how to solve this one? Okay, please read through and understand. Okay, the first part, I try to figure it out. Okay, remember that we must have the projection, right? Projection in x and y direction when we consider this as the curve. So let's draw the projection. Okay, make it big lah, yeah. Okay, this is projection in horizontal and this is projection in vertical direction. Okay. So, to find the horizontal force, okay, for horizontal force, which is, as I explained before, which is F equal to gamma HC multiplied with the area. Okay. Okay. So from here, how to get the HC? Okay. When we want to solve the horizontal force, where is the horizontal? Where is the horizontal? What do you think? This one, right? This is the horizontal force, which is F, okay, F horizontal or Fx lah. or FH. Okay. So remember that the horizontal force, once we draw this one, the projection, the horizontal force must be like this. Oh, okay, this is the horizontal projection, the horizontal force. Okay, definitely the force will be like this. This is F. Remember previously? So to get here, we must use the centroid. So Fr equal to gamma HCA. So from here, the HC is here. Okay, this is HC. What do you know about HC? What do you think about the HC? You can see here. What is the value of HC class? Any idea? Pardon? I cannot hear. Samuel, what is HC?
1.
Is it 1, doctor?
5 plus 1
5 plus
plus 1. 1.
plus 1. So it is 6. We must consider this and this one. So it is 5 plus 1. So it is 6 meter. Okay, so just substitute here. Alright. So from here, FH equal to the gamma of water 9790, multiply with HC, which is 6, multiply with the area. What is the area? What's the area? The area of this. Area of the projection. This is your projection, must be
2 times 1.
okay. Okay, can you see now? This area. This area. This projection area. So what is the area here? What is the area?
12.
12. 6 multiply with 2. Okay, the answer is 704,880 Newton. That's it. Very simple. Because previously we learned the horizontal force, right? We learned Fr equal to gamma HCA. Now we apply to the curve surface. Okay? Now it is easy because we try to apply what we have learned. Okay? However, for the vertical one, okay, for vertical force, it's just the weight of the block. Okay? Okay. So now, okay, let's see. Okay, you can see now how to draw, yeah? Okay, now we have the weight. Okay, just the weight of the block. That's it. Okay, how to calculate this weight? Because we have the FV. Okay, so definitely F vertical direction equal to the weight. How to calculate the weight? The whole this thing weight. I don't know how to draw. Okay, how to calculate the weight? Any idea?
The cube.
Yes, the cube one.
Minus the curve one.
Yes, perfect. The cube, the overall cube minus the quarter circle, right? So here is basically okay. Weight. Okay, let's expand. The weight is equal to rho GB as I explained before here. Okay, the weight of the block is equal to rho GB. So, or gamma V. Because rho G is gamma. To simplify, gamma of the water is 9790. The volume of the cubic, volume of the rectangular minus what? Minus quarter 1/4 quarter of the circle. Sphere, sorry. Sphere. Okay. It's very simple. 9790. Okay. So 9790, the volume of the rectangular is 2 multiply with, okay, you can see 2 here multiply with 6 multiply with 7. Okay, 5 plus 2. So 2 multiply with 7 multiply with 6 minus with 1/4. The volume of the sphere is pi. Sorry, it is not sphere. Sphere, it is like a ball. It is a circle, sorry. Okay, circle. Okay, pi r squared. Pi r. R basically this one. The radius is 2. 2 squared. Okay. Pi r squared multiply with the depth, which is 6. Okay. You try to simplify, you will get the vertical force to be 637,823 Newton. Alright, that's it. That is the final answer. So basically, in order to solve the cube for the curved surface, in order to get the horizontal force, just apply the formula gamma HCA. Okay, in order to get the vertical one, you need to find the weight of the fluid block. That's it. Okay, for this part, I want to give you homework. Okay, please do. This is I encourage you to do this before we begin the next class. Okay. Have I posted this lecture note in the e-learning class?
Already.
Yes, doctor.
We already printed it.
Yes, yeah.
Yeah.
Okay. Is it include this diagram?
Yeah.
Okay, please do. This is your homework.
Okay, doctor.
Homework for the next class. Okay, let's go move on to the buoyancy. Okay, since we have time. Okay, I believe you have learned before buoyancy during your secondary school. Okay, the buoyancy of submerged and floating body. When we have the object, okay, in the water, submerged in the water, and suddenly you can see that the object floating or stay still in the water. This is due to what? Anyone? This is due to buoyancy force that will push the object upward and balanced by the weight of the object. So this buoyancy force discovered by Archimedes, okay, the law of buoyancy, a body immersed in the fluid experience vertical buoyance force equal to the weight of fluid it displaces. So that means here, okay, he tried to explain the buoyancy force FB is equal to the weight of the fluid it displaces. Okay, later on we will understand what is basically the displaced fluid. A floating body displays its own weight in the fluid in which it floats. This is the same lah. Consider we have the body, arbitrary shape. Alright, and then let assign this is in the water. Okay, this is, let's say this is from here to here. Okay, and this is A, sorry, this is A, this is B, and this is C, and this is D, and this is H, and this is K. Alright, so definitely this body, okay, got the weight. The weight is here. Okay, the weight. So we have the force. Let's say we have the force here. F in Z direction, and we have the counter force. F in Z counter force. Okay. And this is, let's say this is gamma of fluid. Maybe this is water or oil, whatever. So the force on the immersed body are involve the gravity and the pressure of surrounding fluid. So here I want to highlight the upper surface is the vertical component. You can see the upper surface here is the vertical component of force is, okay, Fz, and it is equal to the weight of volume of fluid. A, B, C, H, D. Alright, you can see the Fz here is basically equal to the weight of A, B, C, H, and D. Okay, so Fz basically the same here, equal to this weight volume. Okay, understand here? However, for the lower surface, Fz prime, okay, the vertical component of force is Fz prime. Yes, we know already. And it's equal, okay, it's equal to the weight. What do you think? Of the volume of fluid A, B, C, K, D. Okay, where is it? Okay, this one Fz prime basically equal to A, B, C, K and D. The whole this. Okay, the whole of this. This one. Okay. So that means this one is combination F. Z prime is combination of the yellow color and the purple color. Okay, for the Fz only yellow. This is what you need to know lah, the derivation of the buoyancy. So from here, the difference between the two volume, okay, the difference here between the two volume, okay, basically the volume of the body DHCK. Okay, you can see DHCK. So you can subtract lah. Okay, the whole D subtract with the yellow color, you will get DHCK. That is the difference. This one lah, the one I draw before. This one. Okay, this one. Okay, this color. This is what you get lah, the difference. Okay. Now, look at the buoyancy. Buoyant force is denoted by FB. So FB is vertically upwards. Must be upward, yeah. And equal to, okay, F Z prime minus F Z. So therefore, FB equal to Fz prime minus Fz, at which is equal to the width of the volume of fluid DHCK. This one lah. This is C and this is D. This is H and this is K. Basically, what I would like to highlight here is FB is equal to the displaced volume. This is what the purple color we call as a displaced volume. Okay, so this displaced volume is equal to FB. Alright. Buoyancy force on the antibody is equal to the weight of the displaced fluid. So this is the equation. FB basically equal to the displaced weight of displaced fluid. Okay, this is volume displaced, yeah. And then if the DHCK, the one the purple color, is in equilibrium, W is equal and opposite to FB. Okay, which means that density of the body of the body of the fluid are equal. Okay, this is basically the long one lah. You need to know this part. Okay. So this is the case. If the weight of the body is more than the buoyancy force, the body will sink. Okay, remember, if the weight of the body is less than the buoyancy force, the body will rise until its density and that of the fluid are equal. Okay. This is, for example, like a balloon. Okay. We have a balloon. Okay. The balloon, like a helium gas. You fill with the helium gas and then suddenly the balloon okay, the balloon you try to grab and it is loose, it will move to the air. Until at a certain point, the balloon will stop. Okay, it will not go until the moon. No, it is not possible. The balloon will stop at certain elevation. Why? What do you think? It will stop at very high altitude. Why? Anyone? This one. The balloon rising in the air. Okay. Case of liquid with free surface. Free surface. The body will rise to the surface until we rise. Okay, let's see. I want to show you one pretty quick example. This is balloon. Okay, you try to lose the string, it will move until very top elevation. Okay, this is because, alright, just imagine that this balloon surrounded with the air. Okay, this is air, atmosphere. Okay, and definitely the balloon will have the wick. Okay, wick. This one will have the wick. However, we are living in the atmosphere. Our atmosphere, different altitude, different altitude will have different, anyone? Different what? Different altitude will have different what?
Pressure.
Okay, pressure, and then we have different density, right? Density of the air. The air different density at different elevations. So until this elevation, okay, definitely this balloon will have the buoyancy force, FB. Until at certain elevation, FB is equal to the weight. It will stop. For this one, the balloon keep rising because the weight is greater than buoyancy. Okay, you can see one, the weight, okay, more than buoyancy. Sorry, the weight is less than the buoyancy. Okay, the weight is less than buoyancy. That is why the buoyancy keep pushing upward. Alright, I think that's all. Okay, for the next lesson, we continue on the buoyancy force in the great detail. Alright. About the floating body and example. I think that's all for today. Thank you very much for your time. Any question or have you take your attendance class? Have you taken your attendance?
Not yet, Doctor.
Not yet, yeah. Okay, please scan. I think that's all. Thank you very much. I end my session with Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Doctor.
Okay, welcome.
Doctor. Doctor nanti share slide ni kat e-learning ke?